Now let us derive the expression for derivatives of arc length in Cartesian and parametric form. So for that, consider a Cartesian curve. Now let P be a variable curve with the coordinates x, y. Let Q be a neighborhood point to P with the coordinates x plus delta x, y plus delta y. Let the arc length or the distance between P and Q measured along this curve be equal to delta S. Let delta C be the chord PQ. Now by distance formula, we have delta C is equal to x plus delta x minus x whole square plus y plus delta y minus y whole square. So which you will get delta C whole square equal to delta x square plus delta y whole square. Now I'll divide throughout by delta x. So I'll get delta C by delta x whole square plus 1 plus delta y by delta x whole square. So from this we get delta C by delta x equal to 1 plus delta y by delta x whole square whole to the power half. Now consider, since we want to find the derivative of arc length with respect to x and y, so let us consider delta S by delta x. So now by chain rule we have delta S by delta C into delta C by delta x. So that is delta S by delta x can be written as delta S by delta C into delta C by delta x. So that is equal to delta S by delta C into substitute for delta C by delta x from the previous result. So I'll get 1 plus delta y by delta x whole square to the power half. Now let us consider the limiting case. As Q tends to P, delta x tends to 0. As Q tends to P, delta x tends to 0 along the curve C. So now as delta x tends to 0, delta S by delta C becomes 1. So now taking limit as delta x tending to 0, we get limit delta x tending to 0 of delta S by delta x is ds by dx equal to, this is limit delta x tending to 0 of delta S by delta C into 1 plus delta y by delta x whole square to the power half. So this limit is 1 and limit delta y by delta x is nothing but dy by dx. Hence we get ds by dx equal to 1 plus dy by dx whole square to the power half. So this expression 1 is called as the derivative of arc length with respect to the variable x. Similarly, we obtain the derivative of arc length with respect to the variable y in the same way. Like we consider delta S by delta y and write it using the chain rule as delta S by delta C into delta C by delta y, and continuing this procedure we get delta S by delta y equal to 1 plus delta x by delta y whole square to the power half. We call this as equation 2. So this expression is called as the expression for the derivative of arc length with respect to y. So now let us consider the curve to be a parametric curve with a parameter that is x and y as a function of t. So let us consider x equal to x of t and y equal to y of t. Then ds by dx is equal to ds by dx, from the expression 1 I can write it as 1 plus dy by dx can be written as dy by dt by dx by dt whole square whole to the power half. So that is equal to, I'll take the LCM dx by dt here. So I'll get 1 by dx by dt into dx by dt whole square plus dy by dt whole square to the power half. So now consider the derivative of arc length with respect to the parameter t, ds by dt. So that I can write it using chain rule as ds by dx into dx by dt, which is equal to ds by dx, substitute for ds by dx from this expression and into dx by dt. So dx by dt will cancel with dx by dt and you will get dx by dt whole square plus dy by dt whole square to the power half. So this way I'll call this as 3. Hence 3 is the expression for the derivative of arc length with respect to the parameter